move cables around, so on and so forth, right? So this is like hardcore, not a remote usually attack. But then we have so these you typically are in practice conducted by nation state attackers, and we'll see some examples of this actually. Then slightly below that, so slightly less powerful, is the man in the middle or the in-path attacker. Sorry about the name, but you've seen man in the middle like a bunch of times, and it's kind of like an old sexist term, but it's kind of like the thing to search for if you're going to look for these kinds of attacks. So MITM is the shorthand for it, right? So like man in the middle attacker is basically somebody who can actually see, add, and block packets, right? So if I have, say, two endpoints and the network in between, somewhere in between is the actual evil attacker, and they can do all kinds of things. They can not just sniff packets, but they can inject packets, they can block packets, so on and so forth. There's a slightly less strong attacker model, which is the on-path or man-on-the-side attacker. So this attacker they can sniff, right? So they can actually like look at packets, so they can inspect them. They can even add their own packets, but they can't actually block packets, right? So what the reason it's called on the side is because they don't have the direct ability to block the communication between two different endpoints, but they can actually say sniff and inject their own thing. So it's really like, I guess this is really more the figure of an on-path attacker. So they're on-path because they're able to actually see all the packets. There will be an off-path attacker, which is kind of the last one on the list here, which is kind of in the same location as this attacker. So they're not actually in between the two endpoints, the victim and the other victim, because they're both essentially victims. So this off-path attacker, they can't actually see the network traffic, but they might be able to inject or add their own packets that ends up going to one of these victim endpoints. And finally, there's an on-path but passive attacker. So this attacker can only sniff packets. They can't add or modify or block existing packets. So these are the kind of attacker models that we'll talk about, and we'll see a bunch of examples throughout the lecture on this. Okay, and in particular, we're going to look at this in the context of our different OSI layers, right? So last time we talked about the OSI model. In this lecture, we're going to look at attackers starting from the physical layer to slightly a higher level attackers. So like at the link layer, then we're going to look at attackers at the IP layer and BGP, and then attacks on TCP, and finally attacks on kind of critical application network infrastructure like DNS, and a little bit of HTTP, but your assignment actually has you carrying out HTTP attacks at the network layer. So we won't go too much into that here. Okay, so let's start with the physical link model. So here, the kind of we're going to look at, again, different kinds of attacks that violate all the three things that we care about. Kind of one of the most popular one is violating confidentiality, right? So like the way we're going to do this is by eavesdropping. So eavesdropping is just a way of like sniffing traffic and seeing like what's actually being sent between two different endpoints. And there's different ways you can do this depending on where you are as the attacker, right? So like if you've compromised, say, network infrastructure like routers or switches or access points, you can actually see all the traffic that's going through these particular devices. But we can have other kinds of attackers as well, right? So like we might be on an unprotected Wi-Fi network. We might be on a Wi-Fi network that is actually encrypted with, say, WPA2 with with a shared key. And then we have the non-switched Ethernet and also switched Ethernet. So we already talked a little bit about Ethernet before, and how switches actually kind of tie MAC addresses to particular ports. There's still actually some way for you to eavesdrop on other machines that are connected to this particular switch, namely by forging MAC addresses and essentially tricking the switch into sending you packets instead of a different port. But let's fill in the other ones, right? So if we're on an unprotected Wi-Fi network, what can we actually see as the attacker? What do you think? Yeah, whose packets? All right, everybody's packets. Right. It's like this is like free form, so we can do whatever we actually want, right? So totally okay. Okay, great. So this is everybody's packets. What about so this is kind of the equivalent of the non-switch Ethernet, the Ethernet using a hub. So this is, we can see again, everyone, because basically this is a broadcast, right? So like we're just broadcasting, and then we're hoping that only the right machine listens to our network packets. Okay, what about WPA2, right? So we're on a Wi-Fi network. We have a pre-shared key. That's what the PSK stands for. So who can see whose packets can you see if you're connected as to one of these networks? Can you see anybody's? Yeah, so this is a local network, right? So this is like at home when you have Wi-Fi or even at UCSD, but at UCSD it's a little bit trickier because they're using something other than PSK. But like a home network, when you set up one of these routers, right? Like everybody gets the same shared key. So if you have this shared key, then you're connected to this network, then you can actually get at everyone else's data that's using this same key. So you can actually decrypt. But if you don't have this pre-shared key, then you can still sniff the network traffic, right? There's no way for us to stop you. That's just a physical phenomenon. But you can't decrypt. So essentially, you can't see anybody that is connected and what their actual traffic is. Okay, so everyone, if you have key. Okay, great. So how do you actually do this? How do we sniff packets? Well, one way to do it is to pull up Wireshark the way we did before. So I'm going to just try to, I didn't get a chance to complete one of the demos that I wanted to do, but I will try it nevertheless, because why not? It might actually be fun. Okay, so here I have my good old Chelsea machine. This thing is connected. I lied. Let me connect to it again. All right, let me make sure that this machine is actually connecting to the network. Give me 3, 2, 1, 4 seconds. Okay, so what I did on my local machine, well, on a remote machine at UCSD, I have a port listening on a server listening on port 1337. And then I have a separate laptop that is going to connect to that server and says, hello. And then what I'm going to do is SSH into Chelsea. And I've already turned on the Ethernet device into promiscuous mode. So IP link. So this is the command that I ran a little bit earlier. This basically configures your network interface card, your NIC, to listen to anything, not just things destined for this particular MAC address. So I should be getting traffic from anything connected to this Wi-Fi where I have a pre-shared key. And the way we're going to look at that is with TCP dump. So I'm going to maybe, let's say, well, let's just get some traffic here. And this is kind of like a bunch of traffic between Chelsea and Bushwick. So this is not super interesting. This is exactly because I'm displaying all these things. So a bunch of traffic is being sent between these two machines to just render what you just saw. Let's instead look at, I don't know, well, let's see, host 113. So that's the other machine. We might be seeing network from this machine, but let's see, maybe not. All right. I might be connected to a totally, yes, I'm connected to a different Wi-Fi. Okay. Well, TCP dump is the command line equivalent of, here we go. We're already seeing some stuff. Great. Okay, so I should be seeing, say, if I go to neverssl.com, I should maybe seeing, great, neverssl should be sending some stuff over. I should maybe also be seeing some connection to the other machine. So this, I guess we're just seeing a bunch of ARP traffic. We can try to do port. Great. Well, okay. So we're not seeing anything but ARP, but even that's actually okay, right? So like one of the things that I'm able to get is ARP traffic. I am seeing here some UDP traffic between this machine and the gateway, but I don't know, the thing that I want to get at is you can get this kind of information with your just your laptop. You don't have to be a super advanced attacker to get this data. It's a little bit trickier depending on what laptop you have, but for most, you can turn on this promiscuous mode and then just sniff everything on the network. And you can do the same thing when you're on unwired Ethernet. Okay, but you might not actually be a college student. You might be a real world attacker, right? And like real world attackers sometimes are like really advanced attackers, nation state attackers, and they can actually not just conduct attacks at the network layer, they can do it at the physical layer, right? So they can actually tap physical cables. Does anybody know what this photo is of? So this is from a Wired article. They got a bunch of these photos and a bunch of documents from certain people. Have any of you seen this before? Okay, so this is at 611 Folsom Street in San Francisco. It's at the AT&T headquarters, actually. Right. So what's actually like weird about this photo? Is there anything weird, in particular about the door? Okay, so the roof tile's out. Yes. Okay, so this is a little weird, but this is like not super weird. When this is in a data center, so you're running cables, and it's not too weird to have tiles off. Yeah, right. So like the really weird bit is like these aren't door handles. You can't get into this room. So what the hell is happening in this room? Well, this was the secret room at AT&T, and we have where allegedly the NSA tapped fiber optic cables using these splitters that I have on this slide. So basically what they're able to do is just have these vampire splitters basically take a copy of the traffic that was going over these fiber optic cables, and this traffic was then fed to a bunch of software that was analyzing this network traffic, right? So like what's particularly interesting about, oh no, this is the ugly rendering of the slide. Well, okay, you can kind of still see it, but actually, why don't I pull it up from my browser, because you might as well see it. Also, if you're foreign, pretend you may, I'll say change your name on Zoom, because this is actually a classified document, and we're going to see a few of them. Okay, but that was a slide that was released by Snowden. So let's say, so this is the Prism. Here we go. This is the NSA Prism slide from archive. And what I was trying to show you is, let me see, this slide. Great. So here is a like what's interesting about this slide is it's pointing to like where these alleged wiretaps were happening, and they're happening basically on the coast, right? So like San Francisco's here, and what's interesting about SF is that's where there's a ton of traffic from foreign countries arriving in the US, and then kind of like the thing that the NSA, or at least allegedly is doing with this data is it's feeding it to a bunch of software that lets you essentially search this data for all kinds of different queries. So one of those pieces of software is called the optic nerve. So this is the optic nerve, and so like you also, like on the previous thing, there was also the other coast, right? So there we have traffic coming from the UK, where we have the equivalent of the NSA, which is the GCHQ, right? So like we have basically tapped fiber optic cables and a bunch of data, which is going to software like Xkeyscore. So Xkeyscore is just super duper sweet software where you can just search for, videos, photos, emails, like all kinds of interesting things. And at the time, so this was like, in 2014, where these things were leaked and discussed, they were talking about Yahoo webcam traffic. What's particularly interesting about the Yahoo webcam traffic is that they didn't actually find it to be super useful. Or at least like the agents that were looking at this data found the images a little bit undesirable. And it turns out the reason for this is because a surprising number of people use webcam conversations to show intimate parts of their body to other people. So this is like actually like a pretty big fraction of the things that they were looking at, right? So 7% of the images contained, undesirable nudity. And that's kind of like a lot of traffic if you're thinking about looking at this data as an agent. But I think the bigger point that I want to kind of point out is that, at the NSA and equivalent level, right, there are actually certain attacks that you can carry out that are super interesting. So let's see. What Derek is asking, was this stuff implemented pre-Patriot Act? It was not pre-Patriot Act. So this was post-Patriot Act, at least what we think that those vampire what are they called? The vampire splitters. These were supposedly added in 2002. So this is post 9/11, in response to actually trying to figure out is there interesting data to look at to prevent the next 9/11. Obviously this was abused in so many ways, even though the original maybe goals of these kinds of projects are kind of for legit reasons. So okay, so like the NSA, right, is able to actually go underwater and tap these fiber optic cables. So these are fiber optic cables. This is a photo taken by Trevor Pegland. So he's an artist, but he does really interesting bits, and he has a bunch of really interesting books. So if you're into like spycraft type things, I recommend checking out his books, but also his art, right? It's like he learned how to scuba dive, and then he went to take photos of these undersea cables that were actually tapped by the NSA in the Pacific Ocean. Yeah, so these fiber optic cables go across the ocean, and there's lots and lots of them, and sometimes people are trying to add more to improve, the stuff that's going across continents. And there are definitely parts of, I think, La Jolla that were complaining about these kinds of things. We will not get into shark bites, but I appreciate mentioning sharks in a security class. Okay, so one thing we can do is we can sniff the traffic that's like going through these fiber optic cables, but we can also violate integrity, right? So we can do this at the physical layer, but we can do this also at the network layer. Typically at the network layer is where we carry out these kinds of attacks. And the reason we're able to do this is because kind of the predominant protocol is Ethernet, right? And It actually doesn't really matter. All the other ones are basically in the same kind of boat, but they're completely unauthenticated, right? So if you can inject traffic, you can create an Ethernet frame with any address you want, right? And we saw this last time, that like all a frame has is a bunch of things that includes the, source and destination. And, when you send these things, there's nothing checking like, hey, is your MAC address actually the MAC address of the frame that you're sending? You can just forge whatever MAC address you want and send packets as if you were somebody else. So we're going to see how we're going to use this to carry out semi-interesting attacks, right? So one of the things we can do is we can inject ARP packets, right? So you already saw actually in the network sniffing that we just did that we had a bunch of ARP traffic on my local machine, right? So remember, like ARP is used to map IP addresses to MAC addresses. And the way it works is when I need to figure out like, hey, what is the MAC address of some machine I'm trying to talk to, right? So like last time, what we were trying to do is figure out like what is the MAC address of Chelsea so that we can connect to that local server. The way we do this is we broadcast to the whole local network, hey, please send me your MAC address if you are Chelsea, right? And anybody can actually send responses and say like, I'm this machine that has this IP address. I promise I have this IP address, right? So as an attacker, one thing you can do, right, like when we're in a local network, so even if this is a Chelsea and this is Bushwick, and normally when I ask for 192.168.1.15, Chelsea replies back with like, hey, yep, that's me. This is my MAC address. But as the attacker, as long as I beat Chelsea to that response, I can say like, actually, no, I'm Chelsea, right? And where this gets actually pretty interesting is when you're spoofing the IP, the MAC address, or claiming to be the gateway, right? So like typically in like a local network like the one I have at home, right? What we have, let me just remove my my head from this. Okay, we have, say, these two machines, and these two machines are typically, let me just move it here. Why not? They're typically connected to, a gateway. So on my local network, that's 192.168.1.1, right? And all traffic from my home network goes through this gateway, which is, the little router that I have, right? But like what happens if there's an attacker on the network? Well, this attacker can stay here and they would be, maybe happily connected to the gateway as well, because maybe they're talking to their home server somewhere. But when I connect to the network, so either Chelsea or say Bushwick, what the attacker can do is respond to ARP packets saying like, hey, I'm actually the gateway. So Chelsea will think that I'm the gateway because I said that I actually own 192.168.1.1. So Chelsea will, send me packets instead of the actual gateway packets, right? Because like these frames will be on at this lower Ethernet layer. So I'm going to get packets that were actually meant for the gateway, and then I'm going to, I don't know, inspect those packets before I decide to actually forward them to the real gateway, or modify them in flight to do whatever I want to do. Does that kind of make sense? Or rather, please ask whatever you may be thinking about right now. Okay, so let's start with the first question, which is, what is the gateway? So the gateway is just the modem that connects to the outside network from like your local network, right? So it's usually just your modem. Sometimes it's your modem plus your router all in one, but it's basically the IP address of the machine that connects you to the rest of the internet, right? So everything on your network goes through this thing, right? And kind of like we all have, like if you look at the big internet, we all are basically connecting a bunch of gateways together, but those gateways may actually be, you know, a bunch of other machines that go through it. Yeah, so like if we look for real at when we talk to the internet from the gateway, you know, the IP address this is an internal gateway IP address, but actually like what my machine presents to the rest of the internet is an actual IPv4 IP address. This is one of those internal IP addresses, right? So at least to everybody on my local machine, that looks like the gateway, but this gateway also does translation that with to actual IP addresses, and to everybody, kind of from this point, all these machines look like one machine essentially, right? So it looks like I'm talking to one machine, even though there's actually 3-4 machines. So this is like the network address translation NAT, that we will talk about a little bit next time, but it doesn't really matter to some degree. Even if this was a real IP address, there would still be a gateway that connects me to the rest of the internet, even if you know, say one of my machines had a public facing IP address. So in fact, let me actually, why don't I just pull up a terminal and show you an example of something that's not one of these natted things. So over here at the top, I'm connected to a machine called elk, and this is at UCSD, and this has a public IP address. So if we do if config, you know, we're going to get a bunch of, so let me not show you a bunch of the things that you probably don't care about. Okay, here we go. This might be slightly easier to look at. Let me see. So these are all IPv6. This thing should have an IPv4 address, but I'm not seeing it. Maybe one of you is, but elk.sysnet.ucsd.edu. So the actual IP address of this machine is this IPv4 thing here. If we look at etcresolve.conf, this thing has a name server. And let's see, what is my gateway? I should. I'm not seeing it here. Okay, let's see. Okay, here we go. This is the bridge gateway. Nope. All right, well, the broadcast, I have the broadcast address. So it's typically 172.17 something.1, but I guess I'm not seeing it here. All right, well, I have failed you here. And maybe I'll just show it to you on my local .conf. Well, I guess I don't have it here either. I promise I'm not lying about my gateways. They are real things. Okay, so that was a bad demo. But anyway, there is a gateway. There is it's the thing that ends up where all our traffic goes through. Sorry. Okay. Is that a question, or are you responding to something else? Right. So like with ARP, right? Like all we're saying is like, hey, I actually am this machine that has this IP address. So now anytime there is, so if I've gotten your machine to believe that the IP address of the gateway, which is 192.168.1.1, has MAC address that corresponds to the attacker, right? Like on the wire, we're going to send Ethernet frames. So we're going to send it to this machine because that's the machine that has the MAC address that we know. This thing actually knows that that's the real gateway. So what it's going to do is it's going to strip out the Ethernet frame and then re-encode the frame to target it for this machine with the right IP address still. So it's going to have the IP of the gateway. So there'll be two machines with the same IP address, but that's actually possible on the local network if the attacker is actually being active. Is that how pineapples work? I don't know what pineapples are other than the fruit, but maybe we can talk about pineapple some other time. Okay, so I guess we talked about confidentiality, right? So sniffing traffic integrity. So with ARP spoofing, like we're violating integrity. Jamming is the other interesting bit because this leads to, at least at this layer, some kind of denial of service, right? So it violates our availability property, right? So like, how do we actually jam something, or what does that even mean? Well, jamming is basically at the physical layer, just a physical signal that has certain properties like higher amplitude that can be used to either overwhelm or disrupt like other signals, right? So for example, for radio, this depends on the frequency amplitude, and really like at the end of the day, if you have the most power, you can essentially have a stronger signal than everybody else. And there have been a bunch of interesting attacks on radio devices. So here I have a photo from a paper. So this is a photo of a P25 law enforcement radio. So P25 is a protocol that these radios use to communicate in an encrypted fashion, right? So like cops have these radios, and they want it to be encrypted so that somebody nearby can't listen in on what they're trying to do, right? Like for example, if you're trying to actually enter somebody's house, you probably don't want to tell that person that you're about to do that. The interesting bit is, so okay, like one way you can jam this thing is you can be on the same frequency nearby and just be much louder, so that you essentially take whatever the signal is between these two different, let's say between two handheld devices, and just overpower it so that it listens to you instead of this device, right? So if we're two walkie-talkies, if I'm the attacker, as long as I'm bigger, I can, whatever signal I'm actually sending, I can send a louder signal that interferes with this one, right? But that's typically like not super easy to do. It's and right, like you need to have a much louder radio, and it's not clear that like that will work out because the distance between these two things actually matters, right? So like with radios, we have like the square law where you have to be super close, otherwise we lose power at the power of 2. So x whatever the hell that is, I forget EE stuff. It's been a while. But anyway, the really interesting bit about this protocol is it's using crypto, right? And like they're sending a bunch of packets over radio. Now it turns out that some of these packets are inform whether or not they're essentially things that look like CRC. So they basically say like, hey, is the rest of the packet or the other packets actually well formed? Now it turns out that with these particular radios, that if you just muck with just the right bits, and I think it was on the order of like 16 bits. So if you flip a bunch of those bits so that this particular what's called the NID is corrupted, then the devices will think that the rest of the message is malformed, and not play out whatever that radio is, not try to actually decrypt it, right? So like basically just by mucking with a few bits instead of the full signal, you're able to trick the device into thinking that you've sent a bad packet so it doesn't decrypt it. And what that basically means is two walkie-talkies can talk to each other, right? So this sounds like a super clever attack, and it is. This is a really cool paper. But the really fun bit is they were able to carry out this attack without having like a giant tower that's super powerful. In fact, they bought one of these Girltech IMME little radios that cost $15, and they turned that thing into a jammer that's able to exactly target this NID part of a packet and completely take down these networks. Okay, so that's the stuff that we've been talking about at the mostly physical layer. The other thing that I want to look at briefly is at slightly higher layers, right? So at the network layer and what kinds of attacks we can do there. So again, we're going to look at all different kinds of attacks, starting with spoofing. So with spoofing, what we can do is the same way we spoofed Ethernet frames for ARP, we can do it for IP, right? So like Ethernet frames, IP packets don't have any form of authentication, which means that you can send an IP packet with a source address, whatever you want it to be, right? So this can potentially be anything on the internet. Now, there are obviously things on local networks that make sure that you're not sending packets that this network doesn't, it knows that it doesn't have the IP address for, but at least in most local networks, you can forge the IP address of any machine that's potentially like on this network, right? So you can forge the IP address of anybody that's at UCSD if you're like on the UCSD network, and you might even be able to do it broader than that, but that usually it's much easier to catch those. And you can even do this as an off-path attacker, right? So like as an off-path attacker, right? And if you remember, off-path is I have maybe the victim, two victims. So with an off-path attacker, I'm not actually able to intercept, so I can't inject packets in between and sniff on these packets. But what I can do is, for example, forge the sender IP address and send this packet to the machine here on the right, and this machine might try to actually respond back to this machine's because I've spoofed the address of this machine when I sent the packet over, right? And sometimes that's okay, right? So like it does mean that I can't look at this response, but that might be okay, right? There's certain kinds of attacks that I can carry out without looking at the response just by sending clever requests. Okay, so what might be one of those attacks? Well, one of those attacks is on DHCP, on the DHCP protocol, right? So if you remember, the DHCP protocol is used to configure hosts on a network, right? So this is when I connect to my coffee shop network. I ask basically whatever. I ask the network essentially by broadcasting what is my IP address. This is my Mac. What is my IP address? What should I use as the IP address? Where is the gateway? What's the IP address of the gateway? And potentially even what name server should I use, right? So like the DHCP server responds with all these things. Now what can we do as the attacker? Well, so let's draw this out, right? So we have here my new laptop. I just connected to the coffee shop router. And the first thing that I do is I broadcast, to everybody. What's my IP, right? So this is the DHCP discover message, right? Now, typically what happens is this DHCP server will respond back with like, hey, here's a lease. Your IP address is 192.168.1.17, right? But if there is a local attacker, this attacker can happily respond as well, right? So the attacker can say, actually, yeah, here's your lease. Your IP address is 192.168.1.18. So, we beat this response. And what I'm also going to tell you is what the gateway is. So the gateway is 192.168.1.42, which happens to be the IP address of the attacker. And your name server is actually this as well. So that's And now what happens is whenever this machine tries to talk to network, it thinks this is the gateway. It also thinks this is the name server. So it asks the attacker for DNS information, and it tunnels all network traffic through the attacker, who can then, either forward these things through the AP through the rest of the internet. But for things like, DNS, it can also just reply back with like, hey, if I know you're looking for google.com, well, instead of like telling you the actual IP address of google.com, I'm going to pretend that the IP address of google.com is 192.168.1.42, right? So now, like, when you're trying to connect to Google, you're actually connecting to my attacker machine. Okay. Any questions on this? Is speed really the only thing between tricking the laptop that it's the gateway? So speed is the big factor here. Yeah. So as the attacker, you can just sit on the local network and just constantly broadcast these things. If you get there first, you win. Yeah, and in fact, with a bunch of these things, this is actually the case. Like the actual attacks for the HCP, it's actually pretty much this simple. But for some attacks that we'll see later, you have to go through a little bit more effort. But all these attacks are actually pretty doable. Okay, so I'm going to those were just bullets for what we just said. What I want to move on to is other kinds of attacks. Like, let's think about this a little bit more broadly, right? So, okay, DHCP is one thing, but can I do something by just forging IP addresses, right? So by just setting the source IP address to whatever I want. And the answer is yes, right? So there's like 3 classes of attacks that we can carry out, or even like applications, right? So this can be used for good. So for example, one thing, because we can forge whatever is in an IP packet, we can build network scanning tools, right? So tools like Nmap, Zmap, and I'll show that are able to actually scan the whole internet, right? So they're actually talking to every machine on the IPv4 table, and they can try to figure out, like, are machines actually alive? And if they are alive, like, what kind of servers are running on these machines, right? So like with Nmap, which is a pretty fun one thing you can do is you can figure out, for example, like what ports are open, and even like what OS is running, what particular versions of server is this machine running on, say, port 22, and so on and so forth. And I'm going to show you one example of this with Shodan, not with Nmap, but Nmap is perfectly good. Shodan, I think, is kind of interesting because it's, one second. All right, let me, there we go, back to the browser. So I have it here where this is just a web server, and it scans the whole internet. And one thing we can do is we can just query whatever this thing has indexed, right? So what I did is I just searched for Night Scout. Now Night Scout is kind of an interesting web app. So this is a web application written in Node.js that connects to insulin pumps. Why does my machine decide whenever I move this thing, it screws with everything? Okay, we're back. Right, so this is basically your insulin pump is connected to a web app, and sometimes this web app tells your insulin pump, this is what your blood sugar is at, and you should give this amount of insulin in response to that. So if we search for Night Scout, we're seeing more than 0 things that are publicly accessible machines, right? Like, and we're seeing like for some databases that are just publicly accessible, like a Mongo database, but also web servers, right? So like this is one web server that's somewhere in the UK. There's one in Germany, one in Romania, right? And this is very clearly a web server. So like we can even, like, open it up, and this is somebody's insulin pump. Luckily, it seems like it's not connected to some glucose sensor. So, I mean, I don't know. These kinds of websites are like really useful because they do point out things like this. Like you should really not put your insulin pump on the public network, so they can actually be used for good. But it's also scary, right? Because like that's somebody's insulin pump, and you can totally mess with that and cause direct physical harm. So again, do not go mess with these people's servers. It's super duper illegal and it's super unethical. But you should scan your own local machines and your local network. You do want to figure out like, is my web server or is my database actually publicly accessible, and should it be? So this is kind of like typically used for penetration testing and local kind of attack discovery. But obviously attackers use these, right? So these are used by real attackers. Okay, so network scanning is one typically good thing that we use kind of these unauthenticated parts of the protocol. But they can also be used for evil beyond like, having discovered, some particular machine is online now, might come mess with it. So in particular, one thing you can do by forging source addresses is you can carry out denial of service attacks, right? So you can essentially just overwhelm a server with a bunch of traffic, and it might think that it's getting a real connection, but it's not because you forged the IP address. But it keeps alive this connection, thinking that it should be actually talking to the other person on the other at the other end of the channel. But there is no such other person. We can create as many of these fake channels as we want, and we can take down machines this way. And this happens, right? And it happens not just at the IP layer; it also happens at other layers like BGP. So one thing that I want to briefly talk about is BGP hijacking, right? So we briefly talked about BGP last time. So BGP is a protocol that the autonomous systems that form the internet use to share routing information between these networks, right? So like it's what the protocol we use to share routing information. So each BGP node maintains connections to a bunch of its neighbors, right? So the peers is one kind of neighbor, and there's different kinds of relationships between these BGP nodes. But at the end of the day, what happens is these BGP nodes share routing information and route traffic through each other. Like everything else in this lecture, these routes are unauthenticated, so I can share a route with you and I can totally make everything up about it. And what this means is that if we have a malicious or a malfunctioning BGP node on the internet, it might be providing wrong routing information, and this ultimately results in IP traffic getting redirected to parts of the network that it shouldn't. So this slide rendering also is totally busted. Let me actually pull up the slides on my machine, because that might be the easier way to just show you these two slides. This is the downside of sometimes using LaTeX for slides. All right, so I'm just going to use this, and we are at slide 24. I lied. The ones I uploaded are busted. Let me build the slides. Apologies. CSE 127 private. All right. Okay. Then PDF. All right. There we go. Okay. So I'm going to switch between this and the iPad. Okay, great. So this is what I wanted to show you. So this is a screenshot of a government order. So this was, I think, 2008. Yeah. So this was from the government of Pakistan. They were not super happy with what was on YouTube. So they ordered an ISP, so an internet service provider in Pakistan, to take YouTube down, right? So they basically said like, hey, this video is super not cool, and that's the link of the video. So we would like for you to block these IP addresses 208.65.153.238, so on and so forth, right? So this is a court order, and the people working at the ISP just said, okay, there's nothing we can really do. We're just going to actually abide by this request, and we're going to block these IP addresses, right? The way they did it is by adding new routing information for these IP addresses, essentially black holing them, right? So they said that we have a very fast route to 208.65.153.238 to this particular part of the network, which doesn't actually exist, right? But what happened was when they added these BGP entries, they kind of screwed up, and they had these entries for YouTube that said like, I have a really fast route to YouTube. And what happened is this route information was actually shared, with the neighbors, because that's how BGP works. And then all the neighbors are like, okay, you're trying to go to YouTube. That sounds great. This is how you get to YouTube, right? So, okay, everybody in Pakistan got to YouTube, which was a non-existent place because it got blackholed. But these routes were broadcasted outside of Pakistan. So basically, YouTube went down off the internet for a little while because everybody thought that this is the fastest route to YouTube, right? So like they can really carry out these like pretty intense attacks in this way, and they're not the only ones, right? So this has happened a bunch of times. There are all kinds of parties that are monitoring what's going on with BGP. So here is a screenshot of a separate attack that was observed. So this attack was basically broadcasting connections from the US to locations within the US through Reykjavik and London, right? So they were basically saying like, hey, the fastest way for you to get, from Denver to like Kansas, or really from Chicago to New York is actually through London and Reykjavik. Now, why is that actually super scary when we have these kinds of entries into the BGP routing tables? Right? There's no way that this is actually going to be faster unless there's serious network outages, somewhere in the North American continent. But with a skeptical, hat on, why might it be interesting for somebody to route traffic from, major U.S. cities to outside of U.S. cities and then back? Well, so like, okay, those countries can get the data, right? Exactly. What else? Who else can look at data that's coming from foreign places? There are certain government agencies, right? They're totally not allowed to spy on US citizens. But on traffic from other countries, we're good to go. Totally legal, right? This is, this is just hearsay. There's no like actual proof, but this is kind of the thing that folks that at Renesas, and I think whoever wrote about this ended up actually hypothesizing. It's typically really hard to prove any kind of nation state involvement because they're really good at their job. But the US and Pakistan are not the only places. In fact, the US is like actually like overall pretty good relative to other countries. One other one that I wanted to show you before I show you a live website is an entry from this website from BGP Mon. So this was also quite a while ago. So this was in 2014. But what they were basically observing is they were observing a new change, a new broadcast of like the part of the network 8.8.8.0/24, right? So 8.8.8.8, remember, is the Google DNS, but the /24 is actually like a bunch of the Google uh, IP addresses, right? So what they were basically broadcasting here is like, hey, we actually uh, own these IP blocks, so you should totally forward all the traffic to Google through us. And this was, I think, either the yeah, so this was the Venezuelan government, I think, trying to intercept a bunch of Google traffic. Now, the last bit that I want to show you is an actual website that monitors this stuff. Website is Censored Planet. There are a bunch of other ones. Basically, look at how people muck with. I don't know if they do BGP, but definitely DNS. And you can actually like pay attention to what people are doing and who's censoring whom, right? So this here, there are some countries like China and Iran that are particularly bad, and then there's Russia, who's doing quite a few evil things as well, and India and so on and so forth. But it's kind of everybody. There are very few places that don't do any kind of censoring. Okay, so switching back, before we kind of so far, I guess we've looked at physical network and IP, so physical Ethernet and IP. But there are obviously attacks that we can carry out at higher levels, right? So like at the TCP layer, we have the same problems we've had everywhere else, right? So the TCP session identifier, right? So the source address, source port, destination address, destination port. All of these are things that we can forge however we want. And the other kind of bit that we have to that makes it a little bit harder than just vanilla IP is that when we create a TCP connection, right, we have the three-way handshake. Then what we do is we establish these sequence numbers between the 2 points to set up the circuits. So one thing that you have to do as the attacker, you actually have to guess these sequence numbers. But like, suppose we did guess these things, what can we do? Well, one thing we can do is we can do connection hijacking, right? So if we're on path, so that is, we know the port, we know the sequence number, we can inject data into the TCP connection, right? So I can inject whatever I want into TCP connection. That's pretty bad because that TCP connection might be used to contain, say, HTTP data, which might contain, say, a script that I get your browser to run, right? The other thing that we can do is we can take machines down, right? So what we can do is we can inject packets with the reset bit set, right? So if we inject a reset packet, then we can tear down the connection between the two different endpoints, and then essentially disallow this person access to that particular endpoint. Typically, these are websites, and this is kind of how some censorship is actually performed, right? So the Great Firewall of China kind of injects a reset packets into connections and ensures that you can't access certain particular websites from within China. This can be much, right? I guess the injection can get really, really interesting and more nefarious than just disallowing somebody access to a particular website. So one kind of other interesting bit from the Snowden leaks was the existence of a piece of software called, I guess, Turbine. So Turbine and Turmoil together are used allegedly by the NSA to figure out if the particular person of interest is visiting Facebook, and if that person is visiting Facebook, what they then do is they inject packets that contain malware. So they reply back with a Facebook website, but it additionally contains malware that then is installed on the user's machine, and that's when they get direct access to that particular user's machine, right? So like you can use these kinds of TCP injection attacks to inject and carry out, part of a much more complicated attack. This was done before um, Facebook switched everything to HTTPS. So these attacks were much easier. But I wouldn't be surprised if similar kinds of attacks are still possible. Right. So this is, again, like an advanced target attack. It's not something you can just carry out. But if you're at the nation state level, you can carry out these things. And, there's at least some signal from these leaks that these things have happened. Right. So it's like both super scary, but at the same time, this is kind of awesome. Right. Like carrying out these kinds of attacks is pretty cool. But it could also be pretty uncool. So here I have a screenshot from greatfire.org. So they're an organization that basically try to sidestep the Chinese censorship to allow people within China to access websites that are otherwise blocked for political reasons and other reasons. But they were, like under the attack. So one of the things that happened is that their website was taken down, because if you're at the nation state level, like at the level of China, you can forge packets, and you can do this at like super duper high rates, right? So they were able to create 2.6 billion requests per hour. There's no website that can actually handle this amount of traffic. So they had to like get a bunch of support from a bunch of the friendlier networking infrastructure companies to keep the website up. Okay. So it's worth actually looking at this article. It's still online. You can check it out on greatfire.org. But this was in 2015, so it's a little bit outdated, but it kind of still demonstrates that these things are pretty real and things to be worried about if you're doing things like trying to circumvent censorship systems. This was also these attacks at the TCP layer were also used by the Great Canon of China. So here, what's basically going on is this is the thing that's actually used to carry out the DOS attacks. So basically, the way they're able to like scale out to these like massive number of requests per second is by just using the fact that people browse the web, right? So what happens is we are the global internet. We go through, we're trying to access some website on a Chinese network. And then out of the users that are visiting these websites, one thing we can do is we can essentially get these users by carefully replying to connect to the website that we want to take down, right? So we essentially get these users to perform the attacks on our behalf, and then we take them down, right? So like you just get users that are visiting these things and modifying packets to instead send requests to target websites that they want. Okay. The last bit that I want to talk about is the blind spoofing attacks. So let me switch back to the iPad because that might make it a little easier to actually draw. So in the blind spoofing attacks, our goal as the attacker is to try to convince a victim to open a connection with a spoofed host, right? Because if we do that, then what happens? Why is it bad to create a connection with the spoof host? Well, you keep a bunch of resources on your machine, right? So like if this is, or we get to connect to a spoof host and take the spoofed host down, right? So how do we do this blind spoofing attack? Well, as the attacker, we force the initial three-way handshake from whatever host we actually want from the spoofed host. But as the attacker, we can't actually see the SYN ACK, right? Because we're off path, right? So we're sending a request with the source address of one of our victim, but we're never able to actually see the SYN ACK. So how are we actually able to still create a real connection between the victim and whatever the destination host is. Right? Like we essentially have to be able to guess what the SYN ACK really looks like so that we can do the equivalent of learning what the responder sequence number is. So this attack worked because at least for a while, or in the early days, the TCP spec said like the sequence number that you should use is you should get it from your local clock, right? So like clocks are predictable. We can actually guess what these sequence numbers are by just figuring out what the current time is. You know, we were able to actually create these connections because we're able to figure out what the sequence number is. That's no longer the case. So right now we don't use the local clock to set the sequence number. Instead, we do something slightly better, which is we generate these sequence numbers from a random source. And as long as the source is a good source of randomness, then the chance of us guessing the right sequence number is pretty low, right? So it's 2 to the negative 32, which means that, you know, it'll take lots. So that's like 4 billion, right? Like 1 in 4 billion. To actually guess correctly, it takes a little bit less than that, but it's still actually really hard to get these sequence numbers. Okay, so that's TCP. Now let's move on to higher level attacks. So attacks at the application layer. And the one that I want to talk about is the DNS spoofing attack. So again, DNS is a protocol that's used to map domain names to IP addresses. And one of the important bits of DNS is, you know, it's hierarchical, but also like at each stage of the hierarchy, we cache the queries so that we can respond to new requests, in particular to requests for the same domain name faster than having to always traverse the hierarchical tree. So what are the threats that we should be worried about? Really, there's a handful. That the kind of the most obvious one is that, you know, we may have a malicious DNS server that we're talking to, right? So like one of the other attacks, maybe like the DHCP spoofing attacks, actually trick the victim into thinking that they're talking to a real DNS server when in fact they're talking to a malicious DNS server. So what can this malicious DNS server do? Well, it can respond to any query and lie about responses, right? There's nothing, again, authenticated with these packets. But we can also have, say, a local on-path attacker, right? So this attacker can impersonate a DNS server and send a fake response. We can also have an off-path attacker, right? So an on-path attacker is, again, on-path, so it's in between, so they can actually see the queries. And when we make a DNS query, one thing that we do is we send a query ID. So if we look at the DNS spec, one of the things in DNS in the header, let's see. So the header has the ID, right? So when we send a query, we include the ID, and the server responds back with the same ID, and that's how we know that they're responding to the right thing. So what this means is, for an off-path attacker, we have to guess this query ID, right? So this is a 16-bit query ID. In the original spec, the query ID was incremented with each request. So if I was able to get a hold of one of them, I can basically forge DNS responses forever on afterwards. Nowadays, the random query ID is randomized, but that's actually still not alone good enough. So what I want to do is walk through an attack on DNS. So we're going to spoof DNS responses even when the query ID is actually random. And I'm going to try to do this by getting my machine to let me click on buttons. Okay, great. So I'm going to remove myself just to make it easier. Okay, so what I'm going to draw out here is kind of a typical scenario that we've looked at, which is we have our nice browser. And within the browser or the local network, I have a DNS resolver. So your browser actually has this locally. Your OS has this local resolver too. So does your typical home router, right? So this might be in the same piece of software, but we're gonna just separate it out for simplicity. Okay, so what we're going to do is we're going to try to go to, say, bank.com, and we're going to do this because as the attacker, we're actually running in your browser. So this is kind of a web attacker with a local attacker. So we're kind of like as an attacker, we're living both on your network and in the browser. And what we want to do is essentially convince you that when you go to bank.com, you should go to the attacker-owned server. It doesn't, like, we don't have to be in your browser, but that's like one way to essentially force a query or DNS request to say bank.com, because that's the thing that we want to forge. Okay, so what do we do? Well, we send a query. So this is a DNS query to our local reserver, and the query is for a.bank.com, let's say, and the DNS resolver, let's say, doesn't actually have an entry here, so it doesn't. It can't just reply back. It didn't cache anything. So what does it do? Well, it sends a query to a.bank.com, which is from the .com DNS server. And this thing, when it sends the actual DNS request, it has some query ID, and let's just call that thing abstractly x1. So normally the .com server is happy to respond back with the DNS response with the QID set to x1, and saying ans.bank.com is this IP address. Doesn't really matter what it actually is. But the attacker knows that this query was performed, right? And the way it might know is because the attacker is the one that performed the attack, because they're running in your browser. So what they will actually do is they will respond to your DNS resolver before the .com server replies, right? So this might actually take a while because we may have to ask a bunch of DNS servers. So in the meantime, the attacker is just going to send a bunch of responses, just flood the DNS resolver with a bunch of DNS responses with the actual, nsbank.com set to the attacker IP. But they have to guess the ID, and they're going to do this, for each packet, they're going to send the exact same response, but vary the query ID with, Y1, Y2, so on and so forth, right? So basically, we're just going to send a ton of these DNS responses and hope that we guessed the ID right. Now, because the ID is 16 bits, it would take 65,000 requests to actually, ensure 100% that we guess it right. But so that's a lot of requests that will totally go noticed. In practice, we actually don't need this. We can take advantage of the birthday bound, which basically says that after 2 to the 8, so instead of 2 to the 16 guesses, random guesses, we will likely succeed. So what this means is after roughly 256 responses, we can actually poison this local DNS resolver to think that or the name server for bank.com points to the attacker controlled IP address. So what do we do in response to this? Well, instead of just randomizing the ID, what's the other thing that we can randomize? the port, right? So what we're going to do is we're going to randomize the source port because right now that's the port was always at a predictable location, namely 53. So by randomizing that, we get an additional 16 bits of randomness. And now suddenly it gets much harder to actually carry out this DNS spoofing attack. So this is what your DNS machines would do today. They'd actually randomize both, just one. Okay, so this is the fleshed out version. Let me switch back to the properly rendered slides. So you know, the Kaminsky attack was really interesting, and there's some new attacks that came out actually last week. The SAT attack is one of the things that I pointed to, but these are also attacks that are used in the wild, right? So again, going back to the NSA slides that were leaked by Snowden, you know, they're actually pieces of software on that the NSA developed that will let you do DNS hijacking and poisoning, you know, these DNS entries with whatever targets they actually want, right? So these are real things that are sometimes used in the wild. And kind of, again, going back to the slide that I showed you, these are actually used by, or programs like this are used by countries to this is what I actually meant to show you. Give me 1 second. There we go. So this graph has the attacks on DNS that are used for censorship, right? So these are being carried out all the time. And if you're curious about the DNS, the latest attack on DNS, take a look at the thing that I linked to, or actually read the CCS publication on this, because it's pretty interesting. It's able to carry out similar kind of DNS spoofing attacks, but do so using more clever techniques that be beyond just, you know, brute force trying to figure out the random port and the random query ID. Okay, so this is all I have for today. So I think if I've done anything, or hope to have done anything, is convince you that the internet is totally busted. And we're working with like really, really, really sad protocols. And I'm being maybe a little bit harsh. They're sad from a security standpoint because they were designed before security was even a thing to really think about. So they were designed when we thought that people would play nice, but things have dramatically changed. And you know, next time we're going to look at what are some reasonable network level defenses that you can slap on top of your systems after the fact and try to like detect, if not prevent, some of the attacks that we mentioned today. Okay, I will see you Monday.